As you know, we are at the epicenter of the computer ecosystem, one of the most important industries of the world. And so it stands to reason when new markets has to be created, we have to create it starting here at the center of the computer ecosystem. And I have some surprises for you. Things that you probably wouldn't have guessed. And then, of course, I promise I'll talk about AI. And we'll talk about robotics. The NVIDIA story is the reinvention of the computer industry. In fact, the NVIDIA story is also the reinvention of our company. As I said, I've been coming here for 30 years. Many of you have been through many of my keynotes. Some of you, all of them. And just as you reflect on the conversation, the things we talked about in the last 30 years, how dramatic we changed. We started out as a chip company with a goal of creating a new computing platform. And in 2006, we introduced CUDA, which has revolutionized how computing is done. In 2016, 10 years later, we realized that a new computing approach has arrived. And this new computing approach requires a reinvention of every single layer of the technology stack. The processor is new, the software stack is new, it stands to reason the system is new. And so we invented a new system that on the day I announced it at GTC 2006, no one understood what I was talking about and nobody gave me a PO. That system was called DGX-1. DGX-1, I donated the first one to a nonprofit company called OpenAI. And it started the AI revolution. Years later, we realized that in fact, this new way of doing software, which is now called artificial intelligence, is unlike traditional ways of running software. Whereas many applications ran on a few processors in a large data center, we call that hyperscale. This new type of application requires many processors working together, serving queries for millions of people. And that data center would be architected fundamentally different. We realized there were two types of networks. One for north-south, because you still have to control the storage, you still have to have a control plane, you still have to connect to the outside. But the most important network was going to be east-west. The computers talking to each other to try to solve a problem. We recognized the best networking company in east-west traffic for high-performance computing, large-scale distributed processing, a company that was very dear to our company and very close to our heart, a company called Mellanox, and we bought them 5 years ago, 2019. We converted an entire data center into one computing unit. And you heard me say before, the modern computer is an entire data center. The data center is a unit of computing. No longer just a PC, no longer just a server. The entire data center is running one job. And the operating system would change. NVIDIA's data center journey is now very well known. Over the last 3 years, you've seen some of the ideas that we're shaping and how we are starting to see our company differently. No company in history, surely no technology company in history, has ever revealed a roadmap for 5 years at a time. No one would tell you what is coming next. They keep it as a secret, extremely confidential. However, we realized that NVIDIA is not a technology company only anymore. In fact, We are an essential infrastructure company. And how can you plan your infrastructure, your land, your shell, your power, your electricity, all of the necessary financing around all over the world? How would you possibly do that if you didn't understand what I was going to make? And so we described our company's roadmap in fair detail, enough detail that everybody in the world can go off and start building data centers. We realize now we are an AI infrastructure company. An infrastructure company that's essential all around the world. Every region, every industry, every company will build these infrastructures. And what are these infrastructure? These infrastructure, in fact, not unlike the first industrial revolution, when people realized, GE, Westinghouse, Siemens, realized that there was a new type of technology called electricity, and new infrastructure has to be built all around the world. And these infrastructure became essential part of social infrastructure. That infrastructure is now called electricity. Years later, this is during all of our generation, we realized there was a new type of infrastructure. And this new infrastructure was very conceptual, very hard to understand. And this infrastructure called information. This information infrastructure, the first time it was described, made no sense to anybody. But we now realized it is the internet. And every internet is everywhere, and everything is connected to it. Well, there's a new infrastructure now. This new infrastructure is built on top of the first two. And this new infrastructure is an infrastructure of intelligence. I know that right now, when we say there's an intelligence infrastructure, it makes no sense. But I promise you, in 10 years' time, you will look back and you will realize that AI has now integrated into everything. And in fact, we need AI everywhere. And every region, every industry, every country, every company, all needs AI. AI has now part of infrastructure. And this infrastructure, just like the internet, just like electricity, needs factories. And these factories are essentially what we build today. They're not data centers of the past, a $1 trillion industry providing information and storage, supporting all of our ERP systems and our employees. That's a data center of the past. This is similar in the sense that it came from the same industry. It came from all of us, but it's going to emerge as something completely different, completely separated from the world's data center. And these AI data centers, if you will, are improperly described. They are, in fact, AI factories. You apply energy to it, and it produces something incredibly valuable. And these things are called tokens. To the point where companies are starting to talk about how many tokens they produced last quarter and how many tokens they produced last month. Very soon, we'll be talking about how many tokens we produce every hour, just as every single factory does. And so the world has fundamentally changed. We went from a company, on the day that we started our company, I was trying to figure out how big our opportunity was in 1993. And I came to the conclusion, NVIDIA's business opportunity was enormous. $300 million. We're going to be rich. $300 million chip industry to a data center opportunity that represents about $1 trillion to now an AI factory, an AI infrastructure industry that will be measured in trillions of dollars. And this is the exciting future that we're undertaking. Now, at its core, everything we do is founded on several important technologies. This is real-time computer graphics I'm standing in front of. This is not a video, this is computer graphics. It's generated by GeForce. This is a brand new GeForce 5060, RTX 5060. And this is from ASUS. My good friend Johnny is in the front row. And this is from MSI. And we took this incredible GPU, and we shrunk it in here. Does that make any sense? See, this is incredible. And so this is MSI's new laptop with 5060 in it. GeForce brought CUDA to the world. Right now, what you're seeing is every single pixel is ray traced. How is that possible that we're able to simulate photon and deliver this kind of frame rate at this resolution? Well, the reason for that is artificial intelligence. We're only rendering 1 out of 10 pixels. So every pixel that you see, only 1 out of 10 is actually computed. The other 9, AI guessed. Does that make any sense? And it's perfect. It's completely perfect. It guessed it perfectly. Of course, the technology is called DLSS, neural rendering. It took us many, many years to develop. We started developing it the moment we started working on AI, so it's been a 10-year journey. And the advance in computer graphics has been completely revolutionized by AI. GeForce brought AI to the world. Now AI came back and revolutionized GeForce. So really, really amazing. Ladies and gentlemen, GeForce. You know, when you're CEO, you have many children. And GeForce brought us here. And now, all of our keynotes is 90% not GeForce. But it's not because we don't love GeForce. GeForce RTX 50 series just had its most successful launch ever, the fastest launch in our history. And PC gaming is now 30 years old. So that tells you something about how incredible GeForce is. Let's talk about libraries. At the core, of course, everything starts with CUDA. And by making CUDA as performant as possible, as pervasive as possible, so that the installed base is all over the world, then applications can find a CUDA GPU quite easily. The larger the installed base, the more developers want to create libraries. The more libraries, more amazing things are done, better applications, more benefits to users, they buy more computers. The more computers, more CUDA. That feedback path is vitally important. However, accelerated computing is not general purpose computing. General purpose computing writes software, everybody writes it in, Python or C or C++, and you compile it. The methodology for general purpose computing is consistent throughout. Write the application, compile the application, run it on the CPU. However, that fundamentally doesn't work in accelerated computing, because if you could do that, it would be called a CPU. What's the point of not just changing the CPU so you could write the software, compile the software, run it on a CPU? The fact that you would have to do something different is actually quite sensible. And the reason for that is because so many people worked on general purpose computing, trillions of dollars of innovation. How is it possible that all of a sudden a few widgets inside a chip and all of a sudden computers become 50 times faster, 100 times faster? That makes no sense. And so the logic that we applied is that we could accelerate applications if you understood more about it. You can accelerate applications if you were to create an architecture that are better suited to accelerate, to run at the speed of light, 99% of the runtime, and even though it's only 5% of the code, which is quite surprising. Most applications, small parts of the code consumes most of the runtime. We made that observation, and so we went after one domain after another. I just showed you computer graphics. We also have numerics. This is CuPy numeric. This is CuPy is the most pervasive numerical library. Arial and Shona. Arial is the world's first GPU accelerated radio signal processing for 5G and 6G. Once we make it software defined, then we can put on top of it AI. So now we could bring AI to 5G and 6G. Parabricks for genomics analysis, MO9 for medical imaging, Earth-2 for weather prediction, cuQuantum for quantum classical computer architectures and computer systems, cuequivariance and cuTensor, contraction of tensor mathematics, Megatron. This whole row, this whole column here, consists of all of our deep learning and all of our libraries necessary for training as well as inference for deep learning. This revolutionized computing. And it all started with all these libraries. Not just CUDA, but cuDNN. On top of cuDNN, there was Megatron. Megatron, then TensorRT LLM, and then now lately, this brand new operating system for large AI factories, Dynamo. cuDF for data frames like Spark and SQL. Structured data can be accelerated as well. cuML, classical machine learning. Warp, a Pythonic framework for describing CUDA kernels, incredibly successful. cuOpt, mathematical operations, optimizations, things like traveling salesperson, the ability to optimize highly constrained, large number of variables, type of problems like supply chain optimization. This is an incredible success. I'm very excited about cuOpt, cuDSS and cuSparse for sparse structure simulators. Those are used for CAE and CAD, fluid dynamics, finite element analysis, incredibly important for EDAs and CAE industry. And then of course, cuLitho, one of the most important libraries for computational lithography. Mask making could easily take a month. And that mask making process is extremely computationally intensive. And now with cuLitho, we could accelerate that computation by 50 times, 70 times. As a result, this is going to set the stage, open the world for applying AI to lithography in the future. We have great partners here. TSMC is using cuLitho quite extensively. ASML, Synopsys, excellent partners working with us in cuLitho. So the libraries themselves is what makes it possible for us, one domain of application after another domain of science, after another domain of physics, to be able to accelerate those applications. But it also opens up markets for us. We look at particular regions and particular markets and we say, that area could really be important to transform to the new way of doing computing. If general purpose computing, after all these years, has run its course, why hasn't it run its course in every single industry? So one of the most important industries, of course, is telecommunications. Just as the world's cloud data centers have now become software-defined, it stands to reason that telecommunication should also be software-defined. And so that's the reason why we've taken now some 6 years to refine and optimize a fully accelerated radio access network, RAN stack, that does incredible performance. For data rate per megawatt, or data rate per watt, we are now on par with the state-of-the-art ASICs. And so once we could do that, once we could achieve that level of performance and functionality, then after that we can layer on top AI. And so we have great partners here. You could see SoftBank and T-Mobile, Indosat and Vodafone are doing trials. Nokia, Samsung, Kyocera are working with us on the full stack. Fujitsu and Cisco are working on the systems. And so now we have the ability to introduce the idea of AI on 5G or AI on 6G along with AI on computing. We're doing that with quantum computing. Quantum computing is still at the noisy, intermediate scale quantum, called NISQ. However, there are many, many good applications we could already start to do. And so we're excited about that. We're working on a quantum classical or quantum GPU computing platform. We call it CUDA-Q, working with amazing companies around the world. GPUs could be used for pre-processing and post-processing, for error correction, for control. And so in the future, I predict that all supercomputers will have quantum accelerators, all have quantum QPUs connected to it. And so a supercomputer would be a QPU with QPUs and GPUs and some CPUs. And that would be the representation of a modern computer. So working with a lot of great companies in this area. 12 years ago, we started with perception. AI models that can understand patterns, recognize speech, recognize images. That was the beginning. The last 5 years, we've been talking about generative AI, the ability for AI to not just understand, but to generate. And so it could generate from text to text. We use that all the time in ChatGPT. Text to images, text to video, video to text, images to text, almost anything to anything, which is the really amazing thing about AI, that we've discovered a universal function approximator, a universal translator. It can translate from anything to anything else if we can simply tokenize it, represent the bits of information. Well, now we have reached a level of AI that's really important. Generative AI gave us one-shot AI. You give it text, and it gives you text back. That was 2 years ago when we first engaged ChatGPT. That was the big, amazing breakthrough. You give it text, and it gives you text back. It predicts the next word, predicts the next paragraph. However, intelligence is much more than just what you've learned from a lot of data that you've studied. Intelligence includes the ability to reason, to be able to solve problems that you've not seen before, to break it down step by step, to maybe apply some rules and theorems to solve a problem you've never seen, to be able to simulate multiple options and weigh its benefits. Some of the technology you might have heard about, chain of thought, breaking it down step by step, tree of thought, coming up a whole bunch of paths. All of these technologies are leading the ability for AI to be able to reason. Now, the amazing thing is, once you have the ability to reason, and you have the ability to perceive, that is, let's say, multimodal read PDFs, you could do search, you can use tools, you have now agentic AI. This agentic AI just does something that I've just described all of us do. We're given a goal, we break it down step by step, we reason about what to do, what's the best way to do it, we consider its consequences, and then we start executing the plan. The plan might include doing some research, might include doing some work, using some tools. It might include reaching out to another AI agent to collaborate with it. Agentic AI is basically understand, think, and act. Well, understand, think, and act is the robotics loop. Agentic AI is basically a robot in a digital form. These are going to be really important in the coming years. We're seeing enormous progress in this area. The next wave, beyond that, is physical AI. AI that understands the world. They understand things like inertia, friction, cause and effect. That if I roll a ball and it goes under a car, depending on the speed of the ball, it probably went to the other side of the car. But the ball did not disappear. Object permanence. You might be able to reason that if there's a table in front of you and you have to go to the other side, the best way to do it is not to go right through it. The best way is maybe go around it or underneath it. To be able to reason about these physical things is really essential to the next era of AI. We call that physical AI. And so in this particular case, you're seeing us simply prompt the AI, and it generates videos to train a self-driving car in different scenarios, and I'll show you more of that later. That's a dog. It said, generate me a dog, generate me one with a bird, with people. And it started out with the image on the left. And then the phase after that, we take reasoning systems, generative systems, physical AI, and this level of capability would now go into a physical embodiment. We call it a robot. If you could imagine that you can prompt an AI to generate a video to reach and pick up a bottle, of course you could imagine telling a robot to reach out and pick up the bottle. The AI capability today has the ability to do those things. Well, the computer that's where we're going in the near future. The computer that we're building to make this possible has properties that are very different than the previous. The revolutionary computer called Hopper came into the world about 3 years ago, and it revolutionized AI as we know it. It became probably the most popular, most well-known computer in the world. In the last several years, we've been working on a new computer to make it possible for us to do inference time scaling, or basically thinking incredibly fast. Because when you think, you're generating a lot of tokens in your head, if you will. You're generating a lot of thoughts, and you iterate in your brain before you produce the answer. So what used to be one-shot AI is now going to be thinking AI, reasoning AI, inference time scaling AI. And that's going to take a lot more computation. And so we created a new system called Grace Blackwell. Grace Blackwell does several things. It has the ability to scale up. Scale up means to turn what is a computer into a giant computer. Scale out is to take a computer and connect many of them together and let the work be done in many different computers. Scaling out is easy. Scaling up is incredibly hard. Building larger computers that is beyond the limits of semiconductor physics is insanely hard. And that's what Grace Blackwell does. Grace Blackwell broke just about everything. And all of you in the audience, many of you are partnering with us to build Grace Blackwell systems. I'm so happy to say that we're in full production, but we can also say it was incredibly challenging. Although the Blackwell systems based on HGX has been in full production since the end of last year and has been available since February, we are now just putting online all the Grace Blackwell systems. They're coming online all over the place every single day. It's available in CoreWeave now for several weeks. It's already being used by many CSPs. And now you're starting to see it coming up from everywhere. Everybody's starting to tweet out that Grace Blackwell is in full production. In Q3 of this year, just as I promised, every single year, we will increase the performance of our platform every single year like rhythm. And this year, in Q3, we'll upgrade to Grace Blackwell GB300. The GB300 will increase the same architecture, same physical footprint, same electrical and mechanicals, but the chips inside have been upgraded. It has upgraded with a new Blackwell chip, is now 1.5 times more inference performance, has 1.5 times more HBM memory, and it has 2 times more networking. And so the overall system performance is higher. Well, let's take a look at what's inside Grace Blackwell. Grace Blackwell starts with this compute node. This compute node right here, this is one of the compute nodes. This is what the last generation looks like, the B200. This is what B300 looks like. Notice right here in the center, it's 100% liquid cooled now, but otherwise, externally, it's the same. You could plug it into the same systems and same chassis. And so this is the Grace Blackwell GB300 system. It's 1.5 times more inference performance. The training performance is about the same, but the inference performance is 1.5 times more. Now this particular system here is 40 petaflops, which is approximately the performance of the Sierra supercomputer in 2018. The Sierra supercomputer has 18,000 GPUs, Volta GPUs. This one node here replaces that entire supercomputer. 4,000 times increase in performance in 6 years. That is extreme Moore's law. Remember, I've said before that AI, NVIDIA has been scaling computing by about 1 million times every 10 years. And we're still on that track. But the way to do that is not just to make the chips faster. There's only a limit to how fast you can make chips and how big you can make chips. In the case of Blackwell, we even connected 2 chips together to make it possible. TSMC worked with us to invent a new CoWoS process called CoWoS-L that made it possible for us to create these giant chips. But still, we want chips way bigger than that. And so we had to create what is called NVLink. This is the world's fastest switch. This NVLink here, right here, is 7.2 terabytes per second. 9 of these go into that rack. And those 9 switches are connected by this miracle. This is quite heavy. That's because I'm quite strong. I made it look so light, but this is 70 pounds. And so this is the NVLink spine. 2 miles of cables, 5,000 cables structured, all coaxed, impedance matched, and it connects all 72 GPUs to all of the other 72 GPUs across this network called NVLink switch. 130 terabytes per second of bandwidth across the NVLink spine. So just put in perspective, the peak traffic of the entire internet, is 900 terabits per second. Divide that by 8. This moves more traffic than the entire internet. One NVLink spine across this 9 of these NVLink switches, so that every single GPU can talk to every other GPU at exactly the same time. This is the miracle of GB200. And because there's a limit to how far you can drive SerDes, this is as far as any SerDes has ever driven. From chip, this goes chip to the switch, out to the spine, to any other switch, any other chip, all electrical. And so that limit caused us to put everything in one rack. And that one rack is 120 kilowatts, which is the reason why everything has to be liquid cooled. We now have the ability to disaggregate the GPUs out of one motherboard, essentially, across an entire rack. And so that entire rack is one motherboard. That's the miracle. Completely disaggregated, and now the GPU performance is incredible, the amount of memory is incredible, the networking bandwidth is incredible, and now we can really scale these out. Once we scale it up, then we can scale it out into large systems. And notice almost everything NVIDIA builds are gigantic. And the reason for that is because we're not building data centers and servers, we're building AI factories. This is CoreWeave. This is Oracle Cloud. The power density of each rack is so great. They have to put them further apart so that the power density could be distributed. But really, in the end, we're not building data centers, we're building AI factories. And this is the XAI Colossus factory. This is Stargate. 4 million square feet. 4 million square feet, 1 gigawatt. And so just think about this factory here. This 1 gigawatt factory is probably going to be about, 60 to 80 billion dollars. Out of that 60 to 80 billion dollars, the electronics, the computing part of it, these systems are 40, 50 billion dollars of it. And so these are gigantic factory investments. The reason why people build factories is because you know the answer. The more you buy, say it with me. The more you buy, the more you make. That's what factories do. Okay. The technology is so complicated. And in fact, just looking at it here, you still cannot get the deep appreciation of the amazing work that's being done in all of our partners and all of the companies here in the audience in Taiwan. And so we made you a movie. I made you a movie. Take a look.